In this video, we will be looking at some exponent laws. And we're going to start off with the product rule. And that involves multiplying two terms that have the same base. What do you do with the exponents? So we're going to first write this expression out in expanded form. So what does 3 to the power of 2 mean? It means 3 times 3. And what does 3 to the power of 4 mean? It means 3 times 3 times 3 times 3. So if you look at this, how many 3's do we have in total? We have 2 from here, 4 from here. We can write this as 3 to the power of 6. Now let's go back and look at the exponents. Well, the exponents were 2 and 4, and the exponent became 6. That is us adding the exponents. So the product rule states, if you have the same base, let's call it x, and I have x to the power of a times x to the power of b, I can simplify this as x to the power of a plus b. Next, we have the quotient rule. So what happens if you have the same base, but this time you're dividing your terms? Okay, well, 4 to the power of 6 means 4 times 4 times 4 times 4 times 4 times 4, all over 4 to the power of 2 means 4 times 4. Okay, well, this pair of 4's can cancel out, and this pair of 4's can cancel out. So we're left with 4 4's, which we can write as 4 to the power of 4. Now, how could we have gotten here just from the exponents? The exponents were 6 and 2. Well, 6 minus 2 gives us 4, and that's because 2 pairs canceled out. So our quotient rule states, if you have the same base, let's call it x, and you have x to the power of a divided by x to the power of b, that can simplify to x to the power of a minus b. Next, the power to a power rule. So here we have 5 to the power of 2 all to the power of 3. So this is an exponent to the power of another exponent. Well, 5 to the power of 2 all to the power of 3 means we're going to multiply 5 to the power of 2 3 times. So 5 to the power of 2 times 5 to the power of 2 times 5 to the power of 2. And now, if we use our product rule from above, I can add 2 with 2 with 2 because they're all the same base. And 2 plus 2 plus 2, that is 6. So I added 2 3 times. Well, adding a number multiple times is just multiplication. If I'm adding 2 3 times, I could just do 2 times 3. And 2 times 3 is just the multiplication of those two exponents. So the power to a power rule states if I have, let's say, x to the power of a, and that is all to the power of b, that simplifies to x to the power of a times b. Next, 6 to the power of 2 divided by 6 to the power of 2. Well, the long way, the expanded way, it would be 6 times 6 over 6 times 6. Well, anything divided by itself is 1. So 6 over 6 is 1, and this is also 1. But if we were to use our quotient rule, when we divide, we subtract the exponents. So 2 minus 2 is 0. We know this is true because anything divided by itself is 1, but we also know this is true because of the quotient rule, which tells us the 0 rule. Anything to the power of 0 is always equal to 1. Next, we're going to get into some negative exponents. Now, before I expand this out, I'm just going to use my quotient rule. My quotient rule says I can subtract these exponents. 3 minus 5 is negative 2. So this is what the simplified form would look like. But typically, we do not want negative exponents. So let's see how we can modify this. I'm going to go to that expanded form. 7 to the power of 3 means 7 times 7 times 7, all over 7 to the power of 5, so that's 7 5 times. And now 1, 2, 3 pairs of 7's cancel out. And we're left with 1 over 7 times 7, or 1 over 7 squared. So because there were more 7's in the denominator, That 7 is in the denominator with that positive exponent. So what you will notice here, when we have a negative exponent, we can take a reciprocal of this base and that'll turn your exponent positive. What we could have also done is, if we see that the exponent is higher in the denominator, we could do the denominator minus the numerator, but if we do that, we have to leave the base in the denominator and then 1 as the numerator. So here is our general rule. X to the power of negative a is equal to 1 over x to the positive a. So you take a reciprocal of your base, and then the exponent is now positive. Now, how does this apply if your base is a fraction? Okay, well, let's expand it out. We would have 2 over 3 times 2 over 3 all over 2 over 3 5 times. And again, 2 pairs of them are left. So technically, this is 1 over 2 over 3 to the power of 3. But when you have 1 divided by a fraction, let me write it out this way instead of as a fraction within a fraction. 1 divided by 2 over 3 cubed. Well, how do we divide fractions? By multiplying by the reciprocal. And 1 times anything is itself. So we would have 3 over 2 all to the power of 3. So you'll notice that our fraction has flipped. Now let's do the simplified way by just using an exponent rule. Division means subtracting the exponent, so 2 minus 5 is negative 3. So this can also be written as 2 over 3 to the power of negative 3. And the difference between these two is this is a negative exponent, this is a positive, and this base is the reciprocal of the original. So that's our rule. If I have x over y all to the power of a, I just take a reciprocal of the base, and that'll turn that negative exponent into a positive one. So now let's try to use some of these rules. 2 to the power of negative 3. We need to get rid of any negative exponents for our final answer anyway. So I'm going to take a reciprocal of 2. Now technically, we could write this as 1 over 2 all to the power of 3, and then apply that exponent of 3 to the numerator and denominator. But 1 to the power of 3 is just 1, and then 2 to the power of 3 is 8. So whenever your base is an integer like this, I'm not going to bother taking a full reciprocal because I know my numerator will be 1 automatically. So we could have gone straight to this step right here, 1 over 2 to the positive 3. Next, I have x to the negative 1 times y to the negative 2. So I can't do anything with those exponents in terms of uniting them because x and y are different bases, but I can take the reciprocal of each of these to make the exponent positive. And then, instead of writing it like this, I'm just going to unite the fractions because multiplication means multiply the numerators, multiply the denominators. Next, a to the power of 3 times b to the negative 2. A to the power of 3 is fine the way it is, but b to the power of negative 2, we need to take a reciprocal, and there it is, 1 over b squared. And that can be cleaned up as a to the 3 over b squared. So what has happened here, the one that had a negative exponent went down into the denominator. Next, 4 to the power of negative 2 can be written as 1 over 4 squared, and 3 to the power of 2 is just 9. So now we have, or 9 over 1. Now we can do 1 times 9 for the numerator, 4 squared is 16, times 1 is 16. And there we are. Next, some negative exponents with rational or fraction bases. A third to the negative 4, the reciprocal of a third is 3, and now it's the power of positive 4. 3 to the power of 4 is 81. Next, 5 over 3 to the power of negative 2. Well, I'm going to take a reciprocal of the base, so 3 over 5 to the power of 2. This means I need to apply that exponent into the numerator and denominator. So 3 squared over 5 squared. 3 to the power of 2 is 9. 5 to the power of 2 is 25. Okay. For the next ones, we have a fraction, but I noticed that I have some negative exponents in the denominator. Now, I don't want to have a fraction within a fraction. So what I can do, I can imagine that this is 1 over y to the negative 3. And if I reciprocal that, the y to the negative 3 will go up into the numerator, making it a positive exponent. Just like in this example here, when we had a negative exponent in the numerator and ended up being in the denominator, the opposite is true as well. When I take the reciprocal of the y and the z term, because they both have negative exponents, they'll come up in the numerator. So we'll just have x is fine, y to the power of 3, and z to the power of 2. Now in the next one, a to the negative 4 has a negative exponent and the d term has a negative exponent. They have to be flipped in the fraction. Everyone else is happy the way they are. So b squared is happy, c to the power of 5 is happy, but a to the negative 4 needs to come down into the denominator, and it's now a to the positive 4. And d to the negative 7 has to go up into the numerator, and now it's positive 7. Next, 2 to the power of 2 times 2 to the power of 3. This is our product rule. The product rule says add the exponents, but the base stays the same. It's still 2 to the power of 5, and that's 32. Next, x to the 5 times x to the negative 1. I will use my product rule first. 5 plus negative 1 is 4. And now I don't even have a negative exponent to worry about. Next, I have x's and y's. The x's can be simplified. So x to the 2 times x to the 5. We add our exponents. That's x to the power of 7. And then for the y's, 3 plus 10 is 13. Next, now I have some coefficients. So 2 and 3, they're not the same base, so I can't add any exponents, but I can multiply those coefficients. 2 times 3 is 6. And then m, if you would like, has an invisible 1 as its exponent. So keep that in mind, because when we apply the product rule to the m's, we'll have 1 plus 3, which is 4. And for the n's, 6 plus negative 8 is negative 2. Now, it is not okay to leave this as our final answer. We need to fix the n term because it has a negative exponent. And how do we do that? By taking a reciprocal, which means n will end up in the denominator. And there we are. Now we have 3 to the power of 7 divided by 3 to the power of 2. Because it's division, we can subtract our exponents. 7 minus 2 is 5. And now we can evaluate 3 to the power of 5. It is 243. Next, we have z to the power of 8 divided by z, or z to the power of 1. Division means subtracting the exponent if you have a common base. So 8 minus 1 is 7. Next, we have a's and c's. So we apply the appropriate rule to the a and appropriate rule to the c. And in this case, it is the quotient rule for both. So for the a's, 6 minus 2 is 4. For the c's, be very careful with your negatives here because you are doing 2 subtract negative 1, which is 3. So it'll be c to the power of 3. These exponents are all positive, so I don't have to worry about anything. For p, now we have multiple rules coming in. I have some multiplication in my numerator, and then because I have a fraction, there's division. So I'm going to clean up the numerator as much as I can, and then I'll do a quotient rule. So the 3 has no one to be multiplied with, and then d squared times d to the power of 1, 2 plus 1 is 3, and then w to the power of 8 times w to the power of 3, 8 plus 3 is 11. All over 4d to the power of 6, w to the power of negative 2. Now, the 3 over 4, if I divide them, I get a decimal, which I don't want. So I'm just going to keep it as 3/4. And then I'll put the rest of my terms in the numerator or denominator. Now, depending on how I subtract my exponents, it will determine where I should put that specific variable. So for example, for d, If I do 3 minus 6, I will do d to the power of negative 3. And then for w, 11 minus negative 2, that is going to be 11 plus 2, which is 13. That's fine. But if I wanted to, and I notice, wait a second, for d, 3 minus 6 is a negative. If I preferred, for d, I could have started with 6 minus 3. But if I were to do that, because I'm starting from the denominator, I'd put d in the denominator. And then for w, I'm happy to do 11 minus negative 2. So I would put 13 in the numerator. Now that could be a little faster because we get to the proper form right away. For the way I showed it first, well, I have a problem with d to the power of negative 3. So how do I fix that? By taking the reciprocal and bringing that term into the denominator. And then we would end up with the exact same result. So your choice how you want to deal with it. Next, we have the power to a power rule. So 7 to the power of 2, all to the power of 3. Well, when it's an exponent to the power of another exponent, we multiply. So 2 times 3 is 6. And now a 7 to the power of 6 is 117,649. Now, if I have multiple terms in my bracket, like x to the power of 1 and y to the power of 5, all of that is to the power of 4, I have to make sure I distribute that 4 to every variable in the bracket with multiplication. So for x, 1 times 4 is 4. For y, 5 times 4 is 20. Now, if there's a coefficient involved, that 3 has to be applied to the 2 as well, because remember, it has an invisible 1 on top. So this will become 2 to the power of 3, and then 8 to the power of 9 times 3, which is 27. And 2 to the power of 3 is 8. So there we are. For t, I have a fraction in my bracket and then an exponent on the outside. The order you apply your rules in, there can be variations, there can be different orders. I, most of the time, like to clean up what's inside the bracket first. So I'll have 2, and then p cubed divided by p, or p to the 1, is p squared. And then I'll take that and raise it to the power of 4. So I'll have 2 to the power of 4, which is 16. And then p, we multiply the exponents. 2 times 4 is 8. Next. Now we have rules where there are more rules involved. So when we look at u, the first thing I notice is I have these two brackets with exponents on the outside. So I have to deal with that first. So 3x squared y cubed will stay the same. But for that other bracket, we'll have 4 to the power of 3, which is 64, x to the power of 15, because 5 times 3, and then y to the power of 3. Over 2 to the power of 3 is 8. Then we'll have x to the power of 3 and y to the power of 2 times 3, which is 6. So I've cleaned up my power to my power rule. Now I'm going to clean up the product rule in the numerator. 3 times 64 is 192. For the x's, we add the exponents. 2 plus 15 is 17. For the y's, 3 and 3 is 6, all over the denominator. And now, if I can do 192 divided by 8, I will do it, and I can. I get a nice integer of 24. For the x's, 17 minus 3 is 14. And for the y's, 6 minus 6 is 0. But anything to the power of 0 is 1. So for my final answer, I'll just have 24x to the power of 14. Let's try the next one. I have all of my brackets need the power rule. So our first bracket will become a to the 5, b to the 10. Okay, remember there's an invisible 1 here, and we're just multiplying 5 into each exponent. Don't forget the coefficient also gets the exponent of 2, so 4 to the power of 2 is 16. And then the exponents get multiplied. 3 times 2 is 6, 4 times 2 is 8. And 2 to the power of 3 is 8. 8 to the power of 5 cubed will be 15, because 5 times 3 is 15. And then b to the power of negative 4 times 3, which is negative 12. Now that I've dealt with that, I will multiply my numerators. So we'll have 16, a to the power of 5 plus 6 is 11, b to the power of 10 plus 8 is 18, all over 8a, 15, b to the power of negative 12. Now for my coefficients, I can divide. So 16 divided by 8 is 2. For the a's, 11 minus 15 is negative 4. I could have also done 15 minus 11 and then put the a in the denominator. That would be perfectly fine. And careful with your negatives here. 8 minus negative 12 for b is 30. This is nice, but my only problem is I can't finish an expression with a negative exponent. So that a to the negative 4 will have to go into the denominator so that it can have a positive exponent. All right, for the next one. Once again, we have the power to a power rule. So I'm going to distribute that negative 2 in so that we have p to the positive 6, negative 3 times negative 2 is 6. Q to the 2 times negative 2 is negative 4. Then, remember, you have your invisible ones here. So 2 to the power of 4 is 16. P to the power of 1 times 4, and Q to the power of 3 times 4. Then copy paste the denominator because there's nothing to clean up there. Now, once again, I'll multiply my numerators. So 16, and then P's, add the exponents. 6 plus 4 is 10. For the Q's, negative 4 plus 12 is 8. All over that denominator. And now we can finally do our quotient rule. And this time, I'm going to think a little bit more carefully about how I should subtract my terms. So I have 16 over 5. That can't change. It's going to give me a decimal. Then for the p's, 10 minus negative 3 will give me a positive exponent. So I'm happy with that. And then for the q's as well, 8 minus negative 2 gives me 10. So this is great. All my exponents are positive. So that's nice. And two more examples here. So here we have lots of exponents. I have an exponent outside this bracket and I have an exponent outside the big bracket. And I like to work from the inside out, again, in most scenarios. So I'm going to keep that outside 3 there for now. Now, if we look at this numerator, this exponent on the outside is negative. And although I'd have no issue multiplying the negative 2 into these two exponents, I'd also have 3 to the power of negative 2, which would be 1 over 9. And I don't want to have a fraction within a fraction. So I'm going to do something here. I want this exponent to be positive. That would make my life easier. So I'm going to take this entire numerator and bring it down into the denominator because it's that entire bracket to the power of negative 2. So it's like I'm taking a reciprocal of the entire bracket and bringing it down to the denominator. So we're going to have 3x squared y negative 2 to the power of 2 times x cubed y 5. And then the numerator just has a 1. Now let's see how that's going to clean up. We have 3 squared is 9, x 2 times 2 is 4, y negative 2 times 2 is negative 4. That'll get multiplied by x3, y5. So now 1 over 9. And then for the x's, we're adding the exponent. So 4 plus 3 is 7. Negative 4 plus 5 is 1. And all of that is to the power of 3. And all of my exponents are positive here. So now to finish this up, 1 to the power of 3 is 1. 9 to the power of 3 is 729. X to the 7 all to the 3 is x to the power of 21 because we're multiplying the exponents. And then y to the power of 3. So every single component here got that exponent of 3. All right, final question here. So I see some brackets inside. This bracket has a negative exponent, which I'm not too happy about, but I also have this giant negative exponent out at the front. So different things we can do here. I mean, if we want to turn this negative exponent on the outside positive, we can take a nice reciprocal of this entire fraction to begin with. So let's see what that's going to look like. And like I said, there's different ways to deal with these questions, different orders that you can apply your rules in. This is just what I'm thinking right now. So now the outside exponent is positive. I also notice that I have a negative exponent here, but that doesn't worry too much because I can just distribute that into E and F. There is no coefficient, so I think I'm just going to start cleaning here. So I will have e to the power of 3 times negative 3, so negative 9, f to the power of 4 times negative 3, so negative 12, over 2 times 3 is 6, e to the 4 times e to the negative 2, so we're adding our exponents. 4 plus negative 2 is 2. And then for f, 1 plus negative 5 is negative 4. And all of that is to the power of 2. Now again, I'm going to try to be selective here in the order I subtract my exponents. For the e's, I have negative 9 and 2. If I do negative 9 minus 2, I'll get negative 11. But if I do 2 minus negative 9, I'll get positive 11. So the 6 isn't going anywhere. So if I start in the denominator, when I subtract for the e's, I will have e to the power of 11. Now for f, negative 12 minus negative 4 is negative 8. But if I do negative 4 minus negative 12, that's positive 8. So I'll leave f in the denominator because that's where I started my subtraction. And then 1 in the numerator, all to the power of 2. And finally, let's distribute that 2 into each component. 1 to the power of 2 is 1. 6 to the power of 2 is 36. And then for e and f, we will just double those exponents because of our power to a power rule. So e to the power of 22 and f to the power of 16. And there we are. Each question got a little more involved, a little harder, but we are using all of those rules. So if you're multiplying two terms with the same base, you add the exponents. If you're dividing, you subtract your exponents. If you have a power to another power, you multiply those exponents. And then if you have lots of rules you have to deal with, pick one and start simplifying. Like I said, there's different ways to approach each question. And that's it for our exponent laws.